YouTube channel Cat, and today we will see energy conservation in simple harmonic motion. Okay, so energy conservation in S.H.M. Okay, or simple harmonic motion. Okay, so suppose that this is a block, okay, and it is connected here, and this is a spring, okay, and by the force of this kx, x is the deformation in the spring. Okay, this is of mass m, okay, and by this force kx, this is uh, um, forcing towards its side and applying a force of kx, okay, and because of this simple harmonic motion is there, okay, because of this kx, or kx is a restoring force. Small m mass is doing S.H.M. Okay, so because of this force F or kx force, this block will be doing the simple harmonic motion. Okay, so there will be a mean position, okay, and this will be a another extreme position. This is a extreme position. So this is a mean position, this is one extreme position, and this is another extreme position. Okay, here the deformation will be equal to kx max, maximum deformation, and here kx max. Okay, so how the energy comes in this? Okay, so as we can see, when this is kx max and this is kx max, okay, so this is having a purely potential energy, as velocity is equal to 0, as this block will not be moving. When it will be in the mean position, it will be moving towards this point. Okay, when it is at this point, it will come at this point and will be going towards this extreme point. Okay, another extreme point. So its velocity v is not equal to 0, but as it reaches this extreme point, its velocity will be equal to 0. Okay, so at both the extreme points, same here, when the block is at this point, so when it will be going towards this, its velocity will be maximum here, v max will be at the mean position, and as it goes towards this position, its velocity will be equal to 0, v is equal to 0. Okay, so when it is at this point, this extreme position, one extreme position, its velocity is equal to 0, and energy is equals to potential energy. Okay, and when it is at mean position, its potential energy is equals to 0, as deformation is 0, deformation equal to 0. Okay, so at the mean position, deformation is 0, so potential energy equal to 0. Okay, at the extreme position, velocity is equal to 0, maximum deformation is there. In spring. Okay, so this is the scenario for this. Okay, so as we know that the force in this simple harmonic motion is equal to kx, or it is minus kx. Okay, since it is on this side, this is a restoring force, so we have put it the minus sign. Okay, so what will be the work done? dw is equals to f dx, because of this force, work done because of force F. Okay, so it will be F into dx. Okay, or minus kx into dx. Okay, so if we integrate from 0 to x, work done. Okay, what will be equal to minus kx into dx. Okay, so minus half into kx square. So this is the work done because of this force F. Okay, so work done is equals to minus half into kx square. Okay, and x is from mean position. This is a mean position, this is one extreme position, this is another extreme position. Okay, this is like this, extreme position and extreme position. So from mean position we are measuring this x. Okay, 0 to some distance x. Okay, as here the x is equal to 0 and here this is x equals to x. Okay, and here x is equals to x max. Okay, so 0 to x, work done will be equal to half k x square. Okay, so what will be the potential energy? Potential energy because of this. So as we know that work done is equals to change in potential energy. Okay, so ux minus u0, okay, potential energy final minus potential energy initial is equals to work done. Okay, or minus w. Okay, so potential energy initial was 0 and potential energy final, okay, is equals to half k x square. Okay, so potential energy at x is equals to half k x square. This potential energy is equals to 0 is at the mean position. Okay, so final potential energy it is at x displacement. X is the displacement from the mean position. X is displacement from mean position. Okay, so as x is displacement from the mean position, okay, and so ux will be the potential energy at this point. And what is u0? U0 is the mean position potential energy. Since deformation is equals to 0, okay, or spring is relaxed, so potential energy at u is equals to 0 or x is equals to 0 is 0. Okay, so work done is equals to change in potential energy we have applied, and what we have found that potential energy at x will be equals to half k x square. Okay, so this is for this. Okay, so potential energy at x is equals to 0 came out to be 0, and potential energy at x is equals to x will be now half k x square. So as we know that what is this omega or the angular frequency, it is equal to under root k by m. Okay, so what will be this omega square? Omega square is equals to k by m. Okay, or k is equals to m into omega square. Okay, this angular frequency is equals to under root k by m. So this omega square will be k by m, or k is equals to m omega square. Okay, so potential energy was half k x square, or potential energy will be half m omega square x square. Okay, this is the potential energy at x. Ux is equals to half m omega square x square. Okay, so now as we know that what is the equation in the x axis for this moving block m, x is equals to a sine omega t plus delta. Okay, so this is, suppose that this is the block. Okay, so this is the mean position, and this is the extreme position, and this is another extreme position. Okay, and these are equal. Okay, so suppose that when it is at this position and going at this position, and doing a displacement of x, so how the displacement x or how this displacement in the term of sinusoidal function or the periodic function will be written. This is a periodic displacement of mass m. So this is how the periodic displacement of mass m will be written, that x is equals to a sine omega t plus delta. Okay, this is how the this will be written. Okay, so how the velocity will be written? So dx by dt. Okay, so dx by dt, a cos omega t plus delta. Okay, and differentiation of omega t plus delta will be omega, as delta differentiation will be 0. So a omega cos omega t plus delta. So this is the equation for velocity. Okay, so what will the velocity here of this in the mean position, and here this is how it will be written, that a v is equals to a omega cos omega t plus delta. Okay, so this came out to be that the expression for the velocity came out to be v is equals to a omega cos omega t plus delta. Okay, so this is the expression for the velocity. Okay, so as we know that the what was the function of x? X is equals to a sine omega t plus delta. So the potential energy was half k x square. Okay, so this came out to be half k a square sine square omega t plus delta. So this is the sinusoidal or the variable potential energy. Okay, so how the potential energy will be changing when the x will be changing or when the time will be changing. So this is how the potential energy will be written. Okay, so when the system is at rest and when the system is at extreme position, it will be at rest. Okay, so when it is a all the energy is in the terms of this potential energy. Okay, so maximum potential energy will be there. So u max, what will be u max? U max will be half k a square, as this term will be equal to 1. Okay, at extreme position, sine square omega t plus delta. Okay, so u max will be half k a square at the extreme position, and this extreme position also potential energy will be this. Okay, so this is how this will be written, potential energy. Okay, so how the kinetic energy will be written? Half m v square. So this is the kinetic energy, we know kinetic energy. Okay, but the function of velocity is a omega cos omega t plus delta. So the kinetic energy function becomes m half m a square omega square cos square omega t plus delta. So this is how the velocity or the kinetic energy will be changing in terms of time. Okay, so in the one time period, how the velocity will be changing in that time period, this is how it will be written. So maximum velocity will here will be, velocity will be equal to a omega. Okay, as the amplitude is a omega of this function, so maximum amplitude or the maximum it can reach till a omega. Okay, and the maximum kinetic energy is half m a square omega square. So this is the maximum kinetic energy which will be at the mean position, or when x is equals to 0. Energy is purely kinetic energy. So this is how it will be written, the kinetic energy and also the potential energy. So total energy is equals to kinetic energy plus potential energy. So what is the kinetic energy? Half m a square omega square cos square, okay, omega t plus delta. So this was the kinetic energy we found. Okay, and what is the potential energy? Potential energy was half m omega square a square sine square omega t plus delta. Okay, so this is how the both will be written. So half m omega square a square common, sine square omega t plus delta, and plus cos square omega t plus delta. These are the two terms, and sine square theta plus cos square theta is equals to 1. So total energy will be half m omega square a square. So this is the total energy, or E total, half m omega square a square. So this is how the potential energy and kinetic energy will be there of a particular mass which is doing a sinusoidal motion. Okay, that energy will be equal to the half m omega square a square. Okay, so at a particular mean position this will be equal to the kinetic energy. Okay, and at a extreme position this will be equal to potential energy. Okay, but the total energy at any point when it is doing this when it is having this kinetic energy and both potential energy, it will be equal to this only. Okay, so at mean position it is purely kinetic, so half m omega square a square. At extreme potential, so half m omega square a square, but at a particular point or a particular distance x, capital X is equals to x, it is half m omega square a square. Sum of both will be remains the same, or the total energy will be always equal to half m omega square a square. Okay, thank you.